All right. So that would be me. And for those of you who were here for the previous session and the session even before that, the big question that everybody has been asking is, what is a quantum advantage problem? I'm going to get to that. But first, just a little bit about me and where I come from. I'm one of the very few people that has a background both in computer science and particle physics. I did my undergraduate work in computer science, my graduate work in particle physics at the University of Rochester. So to me, quantum computing is like, two great tastes that taste great together. So I'm going to give you a very, very simple heuristic for determining when a problem is a good problem for quantum computing. It's this. This is the guy that invented it. He's still around. He's in, I believe it's University College London, David Deutsch. And his statement was, quantum computing will be the first technology that allows useful tasks to be performed in collaboration between parallel universes. I read that to you for a reason, because any kind of a problem where you say to yourself, I wish I could solve this if only I could, there's a million billion decision trees that I would have to make to solve this problem, and I don't want to foreclose any one of them. I'd like to do all of them at the same time. Those are good quantum advantage problems. And we'll talk a little bit about what quantum advantage is and what quantum utility is, which is something people don't spend enough time at, but should, because it helps you understand where you can apply quantum computing. Before I go on, I just want to give one last thing about my background. I am not, unlike the previous speakers, I'm not developing hardware. I'm not developing software. What I do and what my company has been doing for 22 years is advise enterprise users of technology what it's good for. So my job is to understand this stuff far enough in advance that I can give people reasonable recommendations for what to do about it. So for example, in the past year, we've done primary research to find out what people are doing with quantum computing, and we've also recommended to our clients what kinds of problems they should be investing in quantum resources to solve. And we'll talk about all of those things now. First off, as you know from this conference, there's lots more than quantum is not just quantum computing, it's quantum computing, cryptography, sensing, and networking. I'm not going to talk about all of them. I'm only going to talk about quantum computing. But I will share with you some research that we've done recently. We asked enterprise organizations, we go out and do primary research on enterprise organizations and said, which of the following are you using? Well, there you have the statistics. You will note that quantum cryptography, which really what they meant was quantum resistant cryptography, so deploying the NIST algorithms and things like that, that was up at 42%, and then quantum computing is the next up. Now, you may be saying to yourselves, good heavens, who's doing this? Well, you heard a couple examples in the past session where anyone that's doing, for example, anything that has to do with optimization, physical problems, as you'll see, the many-body problem is a really useful and interesting one. People are trying to use quantum for solving in areas like that, and those are some of the examples of what people are using it for. Last but not least, this is basically a little radar chart of, we do something that's called a technology area benchmark. And what we do is track a number of companies, universities, government facilities, kind of a little bit of a finger to the wind. Think of it kind of as the Dow Jones Industrial Average. Like, here's a handful of bellwether organizations. What are they up to? And what you can see by this, you're looking at this and you're going, okay, this is what? A kind of funny shape here. Basically, what it shows you is what you heard from the last session and what you've heard from most of the conference, which is that we are very much in early days. Every week, there is new foundational research getting done around quantum computing, quantum sensing, quantum networking. Every day, practically, you're seeing things like startups getting formed, startups getting funded. You're seeing less of customer acquisitions, less of revenue growth, although that's still happening. So essentially, what the shape of that radar diagram is shows you that we're very early stages, and over time, we'll begin maturing. So that kind of just gives you a sense of what we see in the industry. So people are using quantum computing today, but it's really nascent still. Okay, here we get to the meat of the discussion. what is quantum advantage and what is quantum utility? Quantum advantage, in a nutshell, is anything that a quantum computer can do better than a classical computer. And I think our previous panelists hedged a little bit because what they did was they pegged it to the state of technology, which isn't quite fair, because computer science tells you that there are different problem types, some of which are solvable with classical computers and some of which just flat out aren't. So, you know, everybody's familiar with P, NP, NP complete, and NP hard problems. I say everybody. Everybody who is a computer scientist learns this in about sophomore year. And this is why programmers are not necessarily computer scientists, because they may not have learned that some problems simply can't be solved with classical algorithms. The basic question, that little table says, is it something we can solve in polynomial time? And can we prove that the solution is a solution in polynomial time? And that polynomial time bounding is very, very important. Because if the answer is yes, that's a classical problem. Don't even deploy quantum computing on it. It's not going to help you there. As you get into NP hard, it may or may not be solvable at all, and you may not be able to verify that it's solvable in polynomial time. But there's a whole class of problems called BQP, which are bounded error quantum polynomial time, where you can prove that you can solve them with quantum computers in polynomial time. So that's kind of a superset of these. What you find is that there is a handful of problems that you can either solve or solve-ish, come close to solving, and I'll give you an example of what I mean by that in just a second, in that with quantum computers that you cannot do with classical computers. So what do I mean by solve-ish? We're all familiar, or many of us are familiar with the traveling salesman problem, right? What is the shortest route that ensures you hit every city? Any kind of an optimization problem also focuses on let's arrive at the optimal result of whatever it is. Well, 99 times out of 100, in the real world, you don't actually care what is optimal. You just care optimal above a certain level. And it turns out that quantum computers are exceptionally good at solving for optimal above an arbitrary level of what optimal is. Okay. And so if you want to say, I don't really care what the best route is, but I care that it's reasonably good, you can deploy quantum computers for that. And that's actually an example. Notice that I mentioned quantum utility. I sort of tossed the idea out there and didn't define it. Now I'm going to circle back and define it. A quantum utility problem is a problem that can be decomposed into chunks that are actually quantum advantage. That is really, really interesting. I don't know if you guys are hearing that. In any event, quantum utility means you can use an assist from quantum computing to enable the problem, to enable the solution of the problem. And we'll give you some examples of that, and then we'll talk very, very in depth a little bit about a very special case, which is AI plus quantum. Okay, so here's a nice little table for you. I think most of you are very familiar with, for example, prime factorization. We've talked about this. This is the solution to RSA. We know that this is a quantum advantage problem. This is something that everybody talks about. We talked about NP and NP hard problems like the traveling sales problem. We are fairly confident that if you can express optimal as good enough rather than absolute, you can make great headway with quantum computing. That third one down is very important and relatively new. One of the things that was recently discovered is that you can use quantum computing algorithms to determine whether or not there's a correlation between two seemingly random strings. So what I mean by that is, let's take two things that are completely random. Like, you look at this and you say, okay, social media mentions of Bad Bunny and wheat futures in Russia. And you say, these two things are completely uncorrelated, but if you can determine that there's an underlying correlation, that can be useful in all sorts of applications. So that is actually something that has been recently theoretically proven and is going to start showing up in real-world cases soon. In fact, this was one of the examples that convinced one of my clients to deploy quantum computing. I won't say what industry they were in, but they really cared about finding underlying correlation. Policy hardening is my absolute favorite because this goes back to the David Deutsch quote. What do I mean by policy hardening? Policy hardening is, let's say, hypothetically, here we are in Washington, you work for the government, and you want to know the answer to the question, show me all policies that do not lead to nuclear war. You guys are listening to me going, that's not possible, Johna, there's too many variables. That's exactly the kind of stuff that quantum computing is actually excellent at, possibly with an assist from AI. So the idea is, you know, those multiple parallel universes. In one universe, you meet with the ambassador from a nation that you're having hostilities with. In another universe, you don't meet with them. How does that go? And you can compare and contrast this and see what policies can actually not lead to, say, nuclear war. Or if you happen to be a cybersecurity specialist, you may want to just simply say, how should I develop policies for my organization that don't lead to being breached? So policy hardening is a great use of quantum computers because it's something that you absolutely can't do with classical computers, and you're increasingly able to do with quantum computers. The many-body problem I mentioned, you heard about it. Anytime people are talking about modeling, modeling the weather, modeling water, modeling airflow, that's an example of the many-body problem. It's in use today, and we're starting to see theoretically that it's very likely that that's going to be an ongoing use for quantum. Last but not least, and what I'm going to spend the next couple of minutes talking about is the whole AI plus quantum. And I just want to take a step back because AI and quantum are good at two very different things. AI is great at generating lots of ideas really quickly, some of which are completely insane, but all of which come out, without any kind of constraint. It's also really good at capturing information very quickly. What it's bad at is knowing whether the information is any good or having any real-world feedback that says whether it's right or wrong. Hallucinations are built into AI. Well, and when I say AI, I mean LLMs at the moment. Hallucinations are built into them. You can't, pull them out. You can't extract them out. So basically, AI is great at coming up with ideas and synthesizing the results into something palatable by humans. Quantum is good at doing these massively parallel computations, quickly determining whether an outcome does or does not meet the parameters you've set. So have we met the value that we need for optimization and modeling reality accurately? It's pretty terrible at interfacing with humans. So what you can actually imagine is what we call a layer cake approach, where you might use AI to come up with a whole series of different potential policies, quantum to then see if those policies actually work, and then a feedback loop to continue refining this until you come up with the best series of policies that will not result in nuclear war or your enterprise getting breached or whatever it is your policies are trying to protect you against. So that's actually an example, and that layer cake of AI plus quantum plus AI recursively is actually going to be a very, very powerful technique as time goes on. So I have a whole set of selection criteria. I don't really have time to go through each of them. I will say I went to the trouble of printing out a 45-minute presentation on selection criteria. If anybody's interested, I have 4 copies for people that want it, or you can give me your card and I'll email you one. But in any event, quantum-ready selection criteria say, is any part of your problem, does it decompose into prime factorization? Is it some kind of an optimization problem with a definition of optimal as being better than some arbitrary level? Are you looking to detect correlation between strings? If you happen to work for any of the three-letter agencies, your answer had better be yes. And is there a scenario, does it depend on multiple different starting scenarios trying to guess the outcomes? Again, that's the policy hardening. Is there a modeling component that today is impossible? Predicting the shape of a wave from the forces on the water molecule, something like that. Can AI actually provide an assist in any way, shape, or form? Maybe you can use AI to come up with the ideas that you're using to do the policy testing. And maybe AI is a better solution if your problem doesn't smell like any of the things that for which there is a quantum advantage. So with that, I'm pretty much wrapping up. Again, I have copies of this that go into greater detail on the selection criteria for quantum advantage problems. And thanks very much for listening.